In 2017, scientists officially began an ambitious experiment to photograph a black hole for the first time. A network of
Alright.
radio dishes across 4 different continents joined together to form a giant, planet-sized observatory known as the Event Horizon Telescope. It set its
HT.
sights on 2
Yep.
targets, Sagittarius A star, the supermassive black hole in the heart
In
of
the
our
Milky Way.
and an even bigger one lurking in M87. With a
A
globe-sized telescope,
a
the
mobile one.
EHT should have enough resolution to directly observe the shadow of a black hole's event horizon.
Oh.
It's been over a year.
But
So
now all
where's
the
the follow-up?
baryonic matter revolving around it.
To get some answers, we went back to MIT Haystack Observatory, one of the 2 hubs responsible for processing all of the observing data.
A lot of people wonder, why haven't you released an image yet? There are 3 reasons for that. One is that it took a long time for the data to get here. At each telescope, we record 64 gigabits per second of data. We record throughout the course of a night. So we're talking about several petabytes of data. For the data volumes we're talking about, the internet is insufficient to transport the data. Nothing beats loading up hard drives onto an airplane and shipping them.
And shipping
Not
hard
the
drives
internet
from
is
telescopes in Chile
match
and the
for
South Pole to data
capturing that much
coordinators
data.
just took months.
A second reason is because we're being very careful on the calibration. After the data were shipped to Haystack, the team here started to correlate the data. Once the data were correlated, we handed them off to the calibration and error analysis team to find fringes. For the first time, we had incredibly sensitive detections on all of our baselines. And that means that we could actually start to see all the little bumps and wiggles that were instrumental in nature rather than from the source.
I can show some example here. One of our target, the Sagittarius A star, everything is rotating after 30 minutes, which is really fast. The Event Horizon Telescope is designed to actually catch up the things happening on very short time scales. It takes a lot of time to check
frame rate.
what's happening. For instance, what's the instrumentation effect? What's the actually minor effect or side effect?
And the third reason is we're just being extra careful. We have internal reviews all the time where one team goes ahead and works with the data, and then people who weren't involved in that can look at the results and say, all right, well, did you think about this? Did you try this?
At this stage of the project, the team has a solid enough data set to start putting together images.
The telescope coverage itself covered all of them.
Labeled piece by piece by each of the observatories.
To make images,
And data
there's
decay.
an infinite number of possible images can fit our data set.
Thermal.
And we need to actually find what is the most likely images for these sources. It's like a detective work.
We actually have 4 different teams of people making images, and they're working blindly. So one team makes an image, a second team makes an image, and then at the end we compare them and say, are these consistent?
But that comes with a whole new set of obstacles.
For our Milky Way black hole, Sagittarius A star, there are actually 2 challenges. What we are expecting to see is the structure or the plasma flow around the black hole is dynamically changing. We are supposed to take a movie of the
snapshots.
So that was some challenge for the image reconstruction. Another challenge is that because Sagittarius star is at the center of our galaxy, we are looking through the many spiral arms of our galaxy. That will slightly blur the image of Sagittarius A star. So we also need to mitigate kind of a scattering effect from the interstellar plasma in front of us on the way to the Sagittarius star. If we move on another source, M87, it also has completely different challenge. Because M87 is not in our galaxy, there are some uncertainty.
Before we explain what those are, remember, when it comes to imaging a black hole, scientists can't observe it directly. They're looking at the surrounding matter and light that's being pulled by gravity around the black hole's event horizon. You've probably heard this phrase before. It's the ultimate boundary, the place where
nothing, not even light, can escape.
Nothing, not even light, can escape their gravitational pull.
So a black hole is a star so massive that not even light can escape from it.
Underneath that classic saying is a geometric parameter that underpins how the EHT maps black holes in spacetime. It's called the Schwarzschild radius. Back in 1916, German astrophysicist Karl Schwarzschild was inspired by Einstein's theory of general relativity. And in his free time fighting as a soldier in World War I, he came up with this formula to calculate the radius of a black hole, where m is the mass, g is the universal constant of gravitation, and c is the speed of light. The Schwarzschild radius is the distance from the center of the black hole to the event horizon. That point
he made that equation up while he was in the war.
This works for non-rotating black holes.
He made that up while he was...
But the field has advanced since Schwarzschild with the Kerr metric, which takes black hole speed into account. Ultimately, the radius is key because it helps physicists unlock the size of a black hole, which is pretty important if you're trying to create an image.
Apparent size of the black hole is determined by distance to M87 and how far the black hole is, and also how actually heavy the black hole is, because the size of the black hole is proportional to the mass of the black hole. We have actually very good measurement for the distance,
the mass is
still there is
infinite.
a factor to uncertainties for the mass of the M87.
The size of the shadow is determined by the black hole's mass. The bigger the mass, the larger the shadow. But if the mass is a question mark, that could pose a challenge.
Yeah, because mass is
if
infinite.
we cannot get the shadow, maybe that's suggesting that the current way to measure the mass of the supermassive black hole in many galaxies could be somewhat long, and we need to do calibration.
While the teams are still working on images, they have some guesses as to what the finals might look like.
For Sagittarius star, expected image is very different from, for instance, the famous image from the Interstellar. So we will see it's like a crescent image, one side is brighter, and there's a shadow,
circular
and another side is
sphere.
faint. For M87, we are expected to see both accretion flow falling into the black hole and also jet, which is the plasma flow escaping from the black hole.
Those images are still preliminary and they haven't been released yet, but we expect to have a release of the papers and the images in the late winter or early spring of 2019.
Black holes are basic constituents of our universe, and these monsters are the anchor point in virtually every galaxy. Understanding their formation and dynamics could be the ultimate test of Einstein's theory of relativity, which makes two key predictions. First, that the gravity of a black hole curves space-time and draws everything towards it. And secondly, that the shadow of the event horizon cast by the accretion disk should be circular. Depending on what the final images look like, we might need to update the law of the cosmos.
Everyone believes that something is falling down the black hole or something is escaping black hole, but actually we still don't have any images. We are at a very exciting moment, and actually we can test what people thought about 100 years ago.
My take is that Einstein was probably right. Every time we try to test relativity passes the test. The image of the black hole could change our conception of relativity, or it could confirm it. So you predict that you will see a circular shadow.
The fun fact about Einstein is that
predictable from the distance
if he wasn't born, it would take us like another 100 years to discover relativity.
Shadow at all, but I think that
it's a great thing he discovered it.
There's something there to be seen.
Great fact.
For more science documentaries, check out this one right here.